Okay, Organic Chemistry 2, Chemistry 3111. This is Chapter 20, which deals with carboxylic acids and their derivatives. So besides carboxylic acids, we're going to be looking at other compounds that are related to carboxylic acids, like amides, esters, acid chlorides, and acid anhydrides. And we'll get into all of those things in this chapter. But let's start out with a little introduction. And carboxylic acids are very abundant in nature and found in a huge variety of synthetic pharmaceuticals. Just like I showed you the common names for aldehydes, carboxylic acids have common names. You might remember that if you had a 2-carbon aldehyde, I'll just pencil it in here. If you had a 2-carbon aldehyde like this, I called that acetaldehyde. Well, if you put an oxygen in here, it becomes acetic acid. So acetaldehyde becomes acetic acid. The next one is butanoic acid. Acetic acid, I didn't mention it. I think you probably know. But acetic acid is the major acid that's found in vinegar. It's responsible for that sharp, pungent smell of it. Then if you look at butanoic acid, that's responsible for the rancid odor of sour butter. Yay, they're not really putting carboxylic acids in a very good light, are they? And I'm not being facetious, but if you've ever smelled vomit, and I'm going to assume that most people have, even if they didn't want to, that the acid that you smell there is butanoic acid, so it doesn't have a very nice smell at all. And if you look at hexanoic acid, if you've ever smelled dirty socks, like, Mr. Dion, what is going on here? Yeah, that's what's responsible for that smell is hexanoic acid. And then lactic acid, I'm sure you're all, I'm sure that everybody hearing the sound of my voice has exercised so hard that they've reached their anaerobic threshold at some point in their life, and they've had a buildup of lactate um, on account of fermentation in their muscles, and they get lactic acid. So you probably have heard of lactic acid buildup in the muscles at the anaerobic threshold, but lactic acid is what's responsible for the taste of sour milk. Other ones, I think you all know what aspirin is. So you've all at least heard of aspirin, but aspirin is a carboxylic acid. It's got 2 functional groups in it, doesn't it? It's got a carboxylic acid, a carboxyl group, and it also has an ester in it. And we know why that's widely used. It's a pain reliever. We have this other compound that's used in the treatment of TB, and another one that's used in the treatment of acne. So all kinds of interesting compounds with carboxylic acids in them. And not only are carboxylic acids interesting in nature and in pharmaceuticals, but they're also used in industrial chemistry. The US, it says here, produces millions of tons of acetic acid per year. And what do we make so much acetic acid for? Are people buying that much vinegar? No, not at all. Most of the acetic acid that's produced from this reaction between methanol and carbon monoxide is used to make vinyl acetate, and that's found in paint. So if you've ever bought, you know, latex paint at the paint store, well, it's got vinyl acetate in it. So they need huge amounts of that. And it says here, carboxylic acid derivatives, we could go on for the next hour, but they play a huge role in organic chemistry. I worked as an industrial chemist for 15 years plus, and I can tell you I did lots and lots and lots of reactions with carboxylic acids. Very useful functional group. If you want to name a carboxylic acid, and you have a carboxylic acid that has only one carboxyl group in it, we take the name of the alkane and then we add oic acid to it. So you all know that if you had a 4-carbon, if you had a 4-carbon hydrocarbon, 1, 2, 3, 4, you would call that butane. So what we do is we drop the E and you replace it with oic acid where your carboxyl, because you have a carboxyl group on there. Now a carboxylic acid, the carbon of the carboxyl group has to be carbon number 1. We don't call it 1-butanoic acid. It is by definition going to be carbon number 1 because you can't have an R group here. Otherwise, it would be an ester. And something that we don't talk about a lot in the organic chemistry class for non-chemistry majors is what is called the hierarchy or the priority of functional groups. And I have them shown here. This doesn't come from our book. I took this from another book. But the idea is that if you have a compound, let's say, that has a carboxylic acid in it and it's got an aldehyde in it, how would you describe it to somebody? Would you say it's an aldehyde, Or would you say it's a carboxylic acid? Well, we have a rule for that. And we say the carboxylic acid takes priority. It's got a higher priority. And so you would call the compound a carboxylic acid. Thus, the suffix of the name would end in oic acid. We see that shown right here with this compound. It does have an alcohol in it. We do have an alcohol, and we have a carboxylic acid. But we see that the name of the compound is based off of the carboxylic acid, or sorry, the parent is based off of the carboxylic acid. So we don't call this an alcohol. We just call this OH a hydroxy. So 5-hydroxy-4,4-dimethyl pentanoic acid. So we have that oic acid suffix. And the order of priority of functional groups, it is shown even in the online version of the textbook. If you dig way down at the very back, I think it's the bottom thing after all the chapters, it does talk about the order of hierarchy of functional groups a little bit, but there you go. Well, what do you do if your parent is a ring? All right, what if your carboxyl group of your carboxylic acid is attached to a ring? You might remember when we looked at aldehydes, we said it was called a carbaldehyde. Well, here with a carboxylic acid, what you do is you name it as an alkane carboxylic acid. So you actually put your suffix as just carboxylic acid. So if you have 6 carbons in a ring, 1, 2, 3, 4, 5, 6, this is a cyclohexane, so you just call it cyclohexane carboxylic acid. All right, nothing to it more than that. If you had 5 carbons in the ring, it would be cyclopentane carboxylic acid. And then, of course, just like we saw with aldehydes, there are also common names for carboxylic acids. If you have if you have 1 carbon, we call that formic acid. The systematic name for that would be methanoic acid. I'm going to write it above, methanoic acid. Why would we call it that? Because it's only got 1 carbon. If you have a 1 carbon hydrocarbon, CH4, you call it methane. So you drop the E and you call it methanoic acid. If you have a 2 carbon hydrocarbon, that's called ethane. So you would call a 2 carbon carboxylic acid ethanoic acid. That would be the systematic name, but the common name would be acetic acid, and this is what we will use most of the time. If you had 3 carbons in a hydrocarbon, you call that propane, and so a 3 carbon carboxylic acid would be called propanoic acid. However, the common name, are you ready for this? It's not propan, it's propionic acid. The next one, if you have 4 carbons, you can see where I'm going with this, would be butanoic acid, but the common name is butyric acid with a Y in it. And then we have benzoic acid, of course, which shows up all the time in organic chemistry. For pentanoic acid, the common name would be valeric acid, but I don't think it even shows up in our book. Somebody asked me, do I need to know the common names? The answer is yes. So yes, no common and systematic names for, we'll call it first five carboxylic acid. So let me put the next one, Sandrina. It would be, what did I say it was? Valeric acid. So this one here, if you have 1, 2, 3, 4, 1, 2, 3, 4, 5, the common name would be valeric acid, and the systematic name would be pentanoic acid. All right, first 5. And if you're wondering, hey, are there common names like for 6 carbons and 7? Yes, there are. Don't worry about them. Okay, you don't need to know them in this class. All right, there we go. And I know several of you are doing biology degrees or studying biology currently. And so you might have seen some of these dicarboxylic acids like succinic acid. You've probably heard of succinate and malonate when you're studying the Krebs cycle and glycolysis. And so dicarboxylic acids, I need you to know a few of them. If you are using systematic nomenclature, so this is the systematic way, okay, you just name the alkane and then the suffix you add is dioic acid. So pentane dioic acid. If you had 4 carbons, it would be butane dioic acid, so on and so forth. In fact, that's what this compound would be. This would be, let's scribble it down, butane dioic acid, but we see that it has a common name, which is succinic acid. If you had 3 carbons, you'd call that propane dioic acid. So this is propane dioic acid, but we call that malonic acid. And the last one would be ethane dioic acid. So let me scribble that in, ethane dioic acid. And the common name for that is oxalic acid, and glutaric acid, again, would be pentane dioic acid. Well, there's another one that comes after this. If you have hexane dioic acid, so let me just pencil it in here. So there's 1, 2, 3, 4, 5, 6, like this. You would call this hexane dioic acid, but the common name for this is adipic acid. Adipic acid. And I think it's a good idea to know the common names for carboxylic acids that have two carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. Why? Because they do come up in biology quite a bit. Now, if you're wondering how to remember these, this is another thing that Mr. Dion, I swear on the Bible, that I did not come up with this in any way, shape, or form. It was my students who created this a number of years ago, and it just kind of stuck. So if you're trying to remember oxalic, malonic, succinic, glutaric, and adipic, what they came up with was this. Oh my stars. This is embarrassing. Go away. Okay? That's what they came up with for OMSGA. Okay? Oh my stars, go away. And believe me, they just came up with that during the lecture. Okay? This was a number of years, maybe 5 years ago or something. But that would be oxalic, malonic. So oxalic has 2 carbons. Malonic has 3, 4, 5, and 6. And again, I think I'm repeating myself here, but the reason why it's so good to know these is because they do show up in biology. And many of you are going to take biochemistry, and so they'll come up there. And then some of you will take cell bio. It will probably come up in that class as well. So there you go. You heard it here first. Well, with all that information in mind, let's see if we can come up with some IUPAC names and common names. IUPAC is another way of saying the systematic name, so systematic name, and a common name for each of the following compounds. So let's see. Remember, a carboxylic acid is RCO2H. Sometimes we condense it to just RCOOH, but they both mean the exact same thing. And so we have a carboxyl group here, we have one here, and we have 3 carbons in between. So that means we have something that looks like this. So I'll just draw it at 1, 2, 3, 4, 5. So we just saw this one. It would be, technically you would call it 1,5-pentane dioic acid if you want to put the locants in. So maybe I should have mentioned that on the last slide. I didn't. So you'd call this 1,5 pentane dioic acid. And then if we think, oh my stars, go. So this must be glutaric acid. So that would be the systematic name. Why don't I put that in blue? We'll put that in blue, and then we'll put the common name in red. How about that? So common name would be glutaric. Yeah, glutaric acid. All right, let's try the next one. We've got 1, 2, 3, 4 carbons. So that would be 1, 2, 3, 4. So the systematic name, butane, we replace it with the E with oic acid. So we have butane or butanoic acid. But the common name was butyric acid. And the last one is benzoic acid. So the way that you would name that, I didn't name it as a systematic, or using a systematic way, right? The common name we know is benzoic acid. That's what I would always call it, 100% of the time. Unless I was a teacher, which I am, I probably wouldn't even ever think of the systematic way of naming this compound, which would be benzene carboxylic acid, okay? Using like the cyclohexane carboxylic acid, this would be benzene carboxylic acid. If somebody in the lab ever asked me, hey, can you pass me the benzene carboxylic acid? I would be, what? Oh, do you mean the benzoic acid? Okay, sure. You know, it's a little strange, anyhow. But it is something that we do need to know. The next one, students tend to like these questions more, and I don't blame them, where you just draw a structure given the name. So cyclobutane, carboxylic acid. I think you guys could probably draw a better cyclobutane than I can. There, that's my best square I got. So we have cyclobutane, we put a carboxylic acid group on it. The next one is 3,3-dichlorobutyric, so that means we've got 4 carbons in the chain. 1, 2, 3, 4. There we go. Remember, the carbon of the carbonyl is number 1, and we have a 3,3, what was it, 3,3-dichloro, so 1, 2, there we go, so 3,3-dichloro butyric acid, and what's the last one? 3,3-dimethylglutaric acid. So, oh my stars, go. So that means glutaric acid has 5 carbons. Let's pencil them in here. 1, 2, 3, 4, 5. And then we've got, what was it? 3,3-dimethyl. Oops, that's kind of ugly. There we go, like that. Any questions on nomenclature up to this point? We have one more we're going to try. One more nomenclature problem. Don't hesitate to interrupt me about the rules or anything, or that's not the way I was thinking about this one. Do not hesitate to bother me, or it's not, I mean, you're not bothering me, but don't hesitate to interrupt me at any point. Okay, next one, we just want to give a good old systematic IUPAC name. So we'll put here systematic name like this. Okay, so we're gonna go here. Let's see. We find the longest carbon chain. 1, 2, 3, 4, 5, 6. The 6-carbon hydrocarbon is hexane, so this must be hexanoic acid. Scribble that down. Hexanoic acid. And then we've got a host of methyl groups. We've got 3,3,4,4 tetramethyl. So pencil that in. 3,3,4,4 tetra. 3,3,4,4 tetramethyl hexanoic acid. The next one, let's number it. 1, 2, 3, 4, 5. So this is some kind of pentanoic acid. And we've got a propyl group on here. So we would call this 2-propyl. 2-propyl pentanoic acid. And the last one, is phenylalanine. This is a amino acid. If any of you take biochemistry, and I think that many of you will probably take it in the fall, the half semester course, or sorry, the 1 semester course, this is called L-phenylalanine. Phenylalanine. And you know, something you'll learn is you've probably heard of D-glucose. Well, all of the D sugars are the naturally occurring ones, but with amino acids, all the naturally occurring ones are L. And one of the first things you'll have to do in biochemistry is memorize all of the amino acids. You'll actually have to memorize the structure of this compound. So you're kind of getting a jump on the competition here. Now that would be the common name, but they're asking us for an IUPAC name. I really have to think about this for a second. We've got 1, 2, 3. So this is 2-amino 3-phenyl propanoic acid. So let's write that down. It would be 2-amino 3-phenyl propanoic acid. And the thing is that, remember, even though you've got the amino group on there, I showed you that a carboxyl group was the king of the castle. If we go all the way back to here, you can see that an amino group is lower than an alcohol even. So it's still a carboxylic acid. So let's go back here. Oops, where were we there? The only thing we have left to do is determine whether this stereocenter is R or S. Can I ask you guys to tell me? Could anybody tell me if this stereocenter is R or S? I could do it myself. Let's see. Here we go. Anybody get an answer for that one? All right, well, let's take a look at it. Our lowest priority group is the hydrogen, going in the back like that. So it's lowest priority. The nitrogen is number 1. The carboxyl is 2. The phenyl is going to be 3. So we're going from 1 to 2 to 3. We're going counterclockwise, and thus the stereochemistry is S. So the compound is S2. S2-amino 3-phenyl propanoic acid. And that covers the nomenclature of carboxylic acids. Now, if you're thinking, it wasn't that bad, he told me that there was a lot of nomenclature in this chapter. Well, hold on. We still have to cover the nomenclature of acid chlorides, acid anhydrides, amides, and esters. So there's still 4 more, and nitriles. Sorry, 5 more carboxylic acid derivatives that we have to learn how to name. But before we go into that, I want to go over one more section with you before we take a break, which just deals with the structure and properties of carboxylic acids. You can see right away on this slide that you already know some of the structures and properties of carboxylic acids. For example, everybody who's hearing the sound of my voice, I know you all well enough to know that everybody knows that the carbon of the carboxyl group is sp hybridized, and therefore that carbon is the molecular geometry of that carbon is trigonal planar, right? It's flat as a pancake. Okay, that's good. And another thing that we even went over in Chemistry 3102, if you took that class with me, when we discussed the retention factors, or RFs, of different compounds, we talked about how a carboxylic acid has a very low RF. Why is a carboxylic acid retained to silica gel? Why is it so polar? Well, what happens is that a carboxyl group can actually produce 2 hydrogen bonds between 2 adjacent carboxyl groups. So because carboxylic acids have such extensive hydrogen bonding, they end up having really high boiling points. And the example that's provided in our textbook is if you just look at the boiling point of ethanol. Let me just scribble it in here. So this is just regular old ethanol that's found in, schnapps and beer, okay? Well, this has a boiling point of around 78 degrees Celsius. Whereas if you have acetic acid, which is a carboxylic acid with 2 carbons, it's got a boiling point of 118 degrees Celsius. So we see a significant jump in the boiling point by adding that carbonyl. And since the hydrogen bonding is so extensive with a carboxylic acid, which is kind of neat. Next thing, just talking about the acidity of a carboxylic acid. This is something I always try to get the mantra going with my first year students, is I'll teach them about carboxylic acids, especially in General Chemistry 2. And I know that some of you are my students in General Chemistry 2. I'll say, well, remember, a carboxylic acid is an acid, but it's a weak acid. It's not a strong acid like HCl and H2SO4, but compared to a lot of compounds, it is an acid. It is a proton donor. Again, a carboxylic acid is only a weak acid. But if you put a carboxylic acid in the presence of a strong base, like sodium hydroxide, oh, you bet your bobby socks, the equilibrium is going to lie to the side of the carboxylate. Let's think about this. A carboxylic acid has a pK of around 5, let's say, ish, okay, in that neighborhood, pK of 5 for our acid. Well, the pK of water is 15.7. So what's a weaker acid? The water, the equilibrium is going to lie to the side big time. Remember, in section 6.12 of Organic Chemistry 1, you're probably thinking, Mr. Dion, I don't remember section 6.12 specifically. I wouldn't expect you to. But if you go back in the book, in that section, it talks about proton transfers and how sometimes they can be in equilibrium and sometimes they're irreversible, as is drawn here. And when the difference in pKa between the acid and the conjugate acid is more than 10 log units, then we say that it's irreversible. And so that's why it's written as irreversible. So again, if you take a carboxylic acid and you put it in sodium hydroxide, you just end up with nothing but the carboxylate. It just rips it off. So I bet you're all just can't wait to find out how to name a carboxylate salt. I bet you're just so excited. Well, what we do is we replace the the suffix ic acid with O8. Okay, and first thing you do is list the ion. So, we'll put here first name, first name cation. And so if we take benzoic acid and we make the sodium salt of it, we call it sodium benzoate. So sodium benzoate, we add that that O8 on the end of it. And if you've ever heard of sodium benzoate, I'm sure that you've all heard of it, because I'm sure that most of my students, even if they might not want to admit it, have looked at the packaging on foods and they've noticed some compounds that come up over and over. And sodium benzoate comes up all the time. If you look at, carbonated beverages and things, they'll say sodium benzoate. The reason why foods will have sodium benzoate in them is because it's a preservative. Okay, it prevents the growth of some molds. Anyhow, that's not what today's class is about. Now, going back to this whole idea of a weak acid. Well, I just said that if you put a carboxylic acid in a strong base, it's going to rip off every proton, just rip them all off. However, what happens if you take a weak acid, like a carboxylic acid, and you just put it in water? Well, in that case, you've got an equilibrium, don't you? In water, vinegar, let's say, this is acetic acid right here, it exists in equilibrium between its conjugate base form. So if this is acetic acid, this would be the acetate ion, and its uncharged form. So if we look at the pK of a carboxylic acid, what I taught you in Organic Chemistry 1 is that acetic acid had a pK of around 5. And that's basically where they lie. If we're looking at most carboxylic acids, they have pKs between 4 and 5. But something that you need to be able to understand is, why is a carboxylic acid so much more acidic than an alcohol? Right? Remember we talked about the pK of alcohols like ethanol has a pK pretty close to water, doesn't it? If you look right here, and you compare the pKa of ethanol to acetic acid, we see a difference of what? 17 log units, or sorry, 11 log units. We see a huge difference, 10 to the power of 11. So that means that this is 10 to the power of 11 times more acidic than the alcohol. Well, why would that be? We go back to area, right? This goes all the way back to Organic Chemistry 1. It can't be atom, because the negative charge of the conjugate base, whether it's ethoxide or the acetate, the negative charge in both cases is on an oxygen. However, we can use resonance to solve this, or to provide a rationale for this, because the carboxylate has 2 resonance structures that contribute to the resonance hybrid, whereas ethoxide doesn't have any. That negative charge is localized on the oxygen, and so it's going to be a stronger base, whereas the acetate would be a weaker base. Anyhow, there we go. Something else that you want to know about the properties of carboxylic acids is that electron withdrawing substituents are going to enhance the acidity of a carboxylic acid. Take a look at this. What we're talking about in this example right here, okay, is areo again. If you were to draw the conjugate base of any of these 4 carboxylic acids, let me zoom in maybe. Come on, there we go. If you were to draw the conjugate base of all 4 of these, the negative charge would be on an oxygen. So we can't use atom. They all have 2 resonance structures. We can't use that. So we use induction. And you see that as we add chlorines, which are electron withdrawing, what happens is the pKa goes down and down and down until we get to trichloroacetic acid, which has a pKa of 0.9. Now, why would that be? It's because you've got 3 chlorines withdrawing electron density, and the more electron withdrawing groups you have, the more it stabilizes that negative charge on that oxygen, right? You've got something pulling electron density away like that. Does everybody follow me on the induction rationale? Give me a thumbs up if you follow me on that. Yes, for induction, just get something that's sucking electron density away. It's going to stabilize the conjugate base. A weaker base comes from a stronger acid. Okay, if you follow me on that, then it won't be much of a stretch to follow what's happening here. We see that if we go from chloroacetic acid to So what would this be? 1, 2. So this would be 3-chloropropionic acid to 4-chlorobutanoic acid. So what I'm doing is I'm comparing this acid to this acid and this acid. You see that as the electron withdrawing substituent gets further and further away from the carbonyl carbon, it has less of an effect on stabilizing the conjugate base. And so as the chlorine, which is electron withdrawing, gets further and further away, the pKa increases. It becomes less acidic. And we see the same rationale applied when we look at benzoic acid, son of a gun, when we look at benzoic acid derivatives as well. What if you have a substituent that's para to your carboxyl group? What we see is if you have an electron withdrawing substituent, like these here, like a nitro or a carbonyl, like an aldehyde or a chlorine, those are going to lower the pKa compared to just regular old benzoic acid. So these are all electron withdrawing groups. They stabilize the conjugate base. That's why they're stronger acids compared to if you have electron donating groups, like a methyl via hyperconjugation or a hydroxyl oxygen. These are electron donating groups. It increases the pKa. It becomes less acidic. And these are just some rationale, that we have to cover for, understanding, why some carboxylic acids are stronger acids or weaker acids than other. I have a question for you. Let's say I compared, I'm going to circle this compound in green. So that's called trichloroacetic acid. If you compared that compound to this compound, let's say I had this. Let's say instead of 3 chlorines, you had 3 fluorines, like that. Could anybody tell me which one would be more acidic? Would it be the compound in the green box or the blue box? Which one do you think is a stronger acid?
Blue.
Absolutely, right? Because you get so many electron withdrawing groups. Fluorine's the most electronegative element in the periodic table. And if we look up the pKa of this compound, we see that it's 0.23. So significantly more acidic than trichloroacetic acid. And the reason I bring up this compound, so this is called TFA, is because it's going to come up towards the end of organic chemistry too. It'll come up in a lecture or two in our chapter about proteins and peptides. Before we take a break, why don't we just try one practice problem? And it says here, rank each set of compounds in order of increasing acidity. So these are the two questions. This is A and this is B. We'll start with A. Why don't we try drawing all the compounds first? These are all butyric acid derivatives. So if we've got butyric acid, and butyric acid, like that. The first one is what? 2, 3, or no, 2, 4. So we have, oh, son of a gun, I should have moved this over. Oops, that's not good. Oops, that's not good either. Let's try something different. Come on. There we go. Mr. Dion is so patient with the iPad. Okay, let's see here. So for the first one, we've got 2, 4. So 2, 4 dichloro, butyric acid. The next one's what? 2, 3 dichloro. And the last one is 3, 4 dichloro. 3, 4 dichloro. Could anybody tell me which one of these would be the most acidic? Would it be the first, second, or third? And again, there's no trick questions. Anybody have an idea?
The second one.
You can see the chat, but a lot of people have been answering in that. I don't know.
Okay. Sometimes I have to restart my chat. Thanks. You should tell me that. Yeah. Because sometimes I can't see what you guys are writing. Oh, see, now I just reloaded it, Lindsay, and it works. Thanks. I didn't even see that any of you had answered about the stereochemistry, so thank you for telling me that. Now I can see that a few people typed it in. Great. All right. Yeah, so Karen says this one's the most acidic. I agree. So we'll put here most acidic. And the way that she solved that was using Aereo. She said, well, I can't use atom because the negative charge would be in an oxygen. I can't use resonance. They all have 2 resonance structures. So I must use induction. The more chlorines that I have, and the closer they are to the carboxyl group, which they are here, this is going to be the most acidic. And then this one would be the least acidic. Okay, we can try this again, everybody. Now that my chat hopefully works, if I type, you guys see that? I don't know, maybe yeah, maybe no. Anyhow, if we call these, why don't we call them, I don't know, well, you guys can tell me the names of these compounds. If you have all 5 of these carboxylic acids, they're all benzoic acid derivatives. Does anybody have an idea which one of these would be the strongest acid? Could you describe it or name it? Maybe I'll try reloading my chat a second time here just to be sure.
With the nitro group?
Absolutely, right? Nitro is crazy electron withdrawing. It's a strong electron withdrawing group. And so this will be the strongest. So why don't we call it, we'll call it number 1, Caitlin. Caitlin, do you have an idea which one would be the second strongest?
Would it be the one with the ether? Like,
No, because the ether, remember that oxygen is electron withdrawing via induction. Go ahead.
no, yeah, I remember.
Yeah. So the oxygen is electron withdrawing via induction. But remember with this, it can also donate a ton of electron density. And so this one wouldn't be the strongest, second strongest. What about the one with the carbonyl group on it, right? We can draw a resonance structure where we actually are able to delocalize the negative charge down here. I'm not going to do the entire thing. You can take your time and do that if you want, but this would be the second strongest. And then the bromine would be third because bromine is electron withdrawing. But Caitlin, right, the ether and the methyl, those are both electron donating. The ether can donate electron density directly, and so it's the weakest of all of them. And then the methyl only donates it via hyperconjugation, so it would be number 4. And there you have it, a little bit about structure and properties of carboxylic acids. Quite a bit to know there, and hopefully some of it is new, some of it was reviewed. And so now we're going to take a short break, and we're going to come back, and we're going to talk about some of the ways that we already learned to make carboxylic acids, and I'm going to teach you a couple of new, really neat ways to make carboxylic acids.